Yep. So I made your notes for you. This would be more efficient so that we could all kind of have the same sandbox workspace. So yeah, let's get to it. Uh, hopefully Zach will watch the video. It says to find the inverse first and then graph the function and its inverse. And then we're going to sketch the line y equals x to verify that they are in fact inverses. So there's kind of a lot going on here today. Let's start with what the directions say first, and that is to find the inverse of each function. So in our first one here, what are we going to do? I know it's a little bit from the past, but like, how do we start the process?
Well, swapping all on X and Y.
Mm-hmm. Right. So we're going to give it a quick swap and say then that x must equal 4 minus 2/3 of y. And then after this, it's just kind of basic algebra. And different people would answer the following question different ways, but what would you do next?
Subtract the 4.
Subtracting 4 is a pretty solid move. So that's going to leave us with x minus 4 equals negative 2/3 of y. And then what's the last part?
Divided by negative 2/3.
Mm-hmm.
Side.
Yeah, I mean, there's a lot of different ways to answer this again. If this were an Algebra 1 lesson, I would have you guys all do the following. I would have you first multiply both sides by 3. So a very proper way to do this is to take everything times 3 like this. Again, it's not the only way, but what that leaves us with is 3x minus 12 equals negative 2y. It's nice, clean math if you go about it in this direction. And then what's the last thing we have to do? You divide everything by negative 2. So if you divide every part of this by negative 2, you wind up with a really nice y equals mx plus b situation. That's kind of always what we should be shooting for with this particular. By the way, what family of functions? Sorry that this hasn't come up before, but do you know what family of functions we're working with in that purple oval? It's not quadratics or cubics or cube roots. It's one that you've been doing for years. Starts with an L. Mhm. Yeah. So with linears, we really ought to be thinking about y equals mx plus b, like we did way back in the day. So anyhow, let's get to it. So if I finish the job and quit yapping, I wind up with y equals, or I guess more to the point, let's do f inverse equals, let's make it official. So we have f inverse of x equals, what would the slope be? Negative 3/2. And then the y-intercept would be plus 6. Good. So step 1 is complete. And now what I'm going to do is I'm going to move this up. You can't really kind of do what I'm doing, but I'm going to fudge a little bit and pull this up here. So what we have now is a function as well as its inverse. And then from here, our goal now is to graph them both. And I always go back and forth. Do I want to make a table? I don't really know that I need to make a table with you, just because you're familiar with y equals mx plus b. So I'm going to save the table more for like problems 2, 3, and 4. This one, I feel like we can just y equals mx plus b it. So I'll color code this for you. I'll call this red guy. And this guy, of course, is purple guy. Does that work for you? And how you do it on your own paper is your own business, how you code it. But let's help me out here. To graph the red line, where would I begin my journey? Up 4. Good. So you remember your y equals mx plus b. So it's the number that without the x is, of course, the y-intercept. So up 1, 2, 3, 4. Like this. And then what's his slope?
Down 2, 3.
Perfect words. Down 2, right 1, 2, 3. And then you want to 1, 2, 1, 2, 3. And you guys will probably want to grab a ruler. So I think I'm going to pause the recording here for a moment while we go find the rulers.
Sorry, I should use this.
As long as I get it back. Yeah. So sure.
You're good.
Remember with straight lines, it's not the number of points that you have, it's how far apart they are. So if you didn't want to plot 7, 6 points like I did, that's fine as long as you plot enough that the space between them is sufficient. Back in Algebra 1, I would have explained that to you, that if you graph 2 points and try to make a line and they're right next to each other, chances are your line's going to get off course. So you want to have really distant anchor points. Right? So that's the red line. I think we can call that one done. Are you guys ready to proceed to the other one?
Mhm.
Okay, let's talk about my purple guy. Where do I start that graphing journey?
Both sides.
Up 6. 1, 2, 3, 4, 5, 6. And what's his slope? Mm-mm.
Up 6.
I already went up 6. We're done with that.
Oh, well, then.
We're on the slope now. You may not remember this about me, but if you do go 1, 2, 3, down 3, and left 2, you know that I will very aggressively yell at you. Why?
Because it needs to be positive.
Because that now is a positive slope, right? So remember, you can't have both your motions be negative motions. Down is a negative motion, left is a negative motion. Two negative motions cancel each other out. So of course you can go down 3. That's what I would do, but then I would turn right 2 because I want to make sure that I don't perform another negative motion. And you also could start your journey up 3, 1, 2, 3, and then go back to the left 2. Again, the idea is that you want to make sure at the end of the day that your slope is behaving the way you know it's supposed to. So you grab your ruler and you make a line. And I figured for this particular activity for the day that this would be a good introductory sort of problem for us, kind of a foot in the door to the whole experience. So if you graph the two lines, do they look like inverses?
No.
It's kind of hard to say, and that's where the last bit of the directions come into play. And so the last thing it says in the directions is graph the line y equals x, because inverses are all about y becoming x or x becoming y. So it seems pretty sensible. I talked about this like 2 weeks ago with you, but I wouldn't expect you to remember this. It was just a quick little bleep on our discussion. The whole act of finding an inverse is literally switching x and y. So it makes sense then that they would sort of behave a certain way around the line whose name is quite literally y and x changing places. So what I want you to do now is graph the line y equals x. And that's, of course, a line with a y-intercept of 0 and a slope of 1. And so for this particular line, you would just start in the lower left quadrant and work your way to the upper right quadrant. And that is a line that you'd best be pretty familiar with for the next few days. So that is the line y equals x. The goal here, and again, I have an advantage that I have colors, but the goal here is for you to see that now you can say those do in fact look like inverses. And the idea is like, can any red point be mirrored across that line and have a purple counterpart? And I would venture that the answer is yes. Like, for example, this point that I'm circling in red and this point that I'm circling in purple, you really wouldn't want to deny me that those are perfect mirror reflections of each other, right? So when we talk about our two graphs, our two functions inverses of each other, a visual way, rather than using composition, could I use composition? Sure, I could do f of f inverse and f inverse of f and see if they both come out to equal x. This is a more graphical approach to the same idea. I can actually see that these functions are inverses by graphing them and verifying that every point, every purple point, has a mirror opposite on the other side of the green wall. And it's always, this green wall is always going to be in existence because, again, the act of inverting is literally taking y and setting it equal to x or vice versa. So I don't know how lost you are about that, but that's what we're doing now. The graphs from here on out are just going to get harder, but the idea remains the same. Ready to press on to number 2? So again, we find an inverse algebraically, then we graph dude and his inverse, and then we verify that they're inverses visually by showing that they like a mirror around the line y equals x. Okay. Number 2, again, let's just dive right in and first things first, find the inverse. So let's go. So the first thing we're going to do is swap the y and the x, and we're going to say, so x must equal the square root of y plus 2. And then I got to start going in now and digging that y out. How am I going to do that?
Subscripts.
You cannot subtract 2. He is not free to move about the cabin.
This,
Square first. Yeah, like the captain still has the seatbelt sign on, right? But if we square both sides, then we wind up with x squared being equal to y plus 2. And now everyone's free to move about the cabin. And at this point, if you wanted to subtract 2, you could. So we can now say that g inverse of x is equal to what?
X equals to 2.
Good. So the idea now is that I've got 2 functions. I've got a function and his inverse. Oops, that was the wrong button to pick. I want this button. So I've got a function and I've got his inverse, and I'm going to graph them both now. So this is where I was 50-50 coming into today's lesson. I was just right dead down the middle. Are these kids going to be okay if we use transformations, and or are they going to need a table? I think you're going to be okay with the simple transformations because we have talked about this a little bit. You did a delta math on it where you remember when you had to grab the graph in the middle point and like move it around. So you should be familiar with this. Let's start with g of x. And again, I'll color code them for us. So the g of x will be my red graph. And for me personally, that g inverse will be my purple graph. Let's start with red graph. You guys, and this is a lot for me to ask of you. Do you remember by chance what a square root graph looks like? It spawns itself here and it goes this way, like this. I'm going to pause this real quick. Yes, this is the square root graph. Good memory. So what we're going to do is we're going to remember what that graph looks like, and then we're going to transform all of his points 2 to the left, because that's what the +2 on the inside means. You might or should remember that. So as far as the square root function is concerned, let me zoom in a little bit. I'm not doing the +2, by the way, right now. We're going to deal with that in a second. So I'm going to zoom way in on this. And you'll remember this is where the parent functions are so handy to know. So the graph originally has a point of 0, 0, because the square root of 0 is 0. What's the next main point on a square root graph? 1, 1, because the square root of 1 is 1. What's the next one?
There.
Square root of 4 is 2. And there's only one more really that fits on this size grid. What is it? 8 does not have a nice square root, but it is 9 and 3, like this. So before you sketch the graph, what you're going to want to do now is transform the points one by one. So going back, if I zoom out now, if we look at the function, it says to do that square root graph, but with a +2 on the inside. And you'll remember that that's a sideways backwards one. So we're going to take all the red dots now and we're going to translate them 2 units to the left. So every time I move a dot, I'm going to sort of delete, if you will, his predecessor. So I'm going to take this first origin dot and I'm going to move it 2 jumps to the left to here. And then I'm going to delete original guy. The thing about graphing is like the structure isn't necessarily what's changing. It's like I'm just going to a new build site and rebuilding there. In this case, that's all it is. So I'm going to now move this one left 2 and then delete the OG and then move this one left 2 and delete the OG and do the same thing again. There's great potential that that might be confusing, but there's also great potential that you're like, yeah, we're good. We get it. Are we okay? Okay. Now, the math is generally pretty easy. Trying to graph this is the hard part. So I wish us all luck, and I'm going to try with my writing board to do this, and it's probably going to not go too well. So, and you're going to be doing it on your paper too. So we got this graph here. So there is our first curve. And now we're going to go and we're going to graph the second one. And there are all sorts of conversations we can have about this, about could I have done this? Could I have done that? There's a ton of shortcutty ways to do things, and we'll talk all about that in the coming days. Anyways, in the meantime, I'm going to zoom back out, and now we're going to talk about the purple function. What family is that from? X squared, quadratics, parabolas, right? And so the OG parabola, as you know, would have and I hope you know this, and we didn't spend a ton of time on it, but like the OG parabola would have points here, 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 so on and so forth. You remember these points? So tell me this, how I'm going to undo all those points. How are those points going to get moved
Down two.
down two? And it's easy. I can appreciate the sentiment of saying two to the right, but you got to remember that when it's like an afterthought, like this one is, you see how the minus two is like after the fact. Those are our vertical movers. And so those are the normal ones, nothing backwards about it. So we just take all those would-be dots and we go down two. So I'm going to zoom back in, over here. And then I'm going to graph. I'm going to graph the OG function, except I'm going to graph him at his new down two home. Rather than like plotting and moving, like if you know exactly what you're already up against, just go to the new build site and build it there. It's more quick. So I'm going to go down two, and then I'm going to start the construction of this. And we're going to talk in a second about why this doesn't work, but this is a much more upper level-y conversation. So let's just stick with the graphing so far. So we got 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. And then we got to go again. And I think we should do one more. We should go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Like this.
Ooh.
Do those look like inverses to you? What a loaded question. They are, but we have to fix something first. There's something that I've been avoiding for a long time. We have to do something called restricting the domain. I feel like it's popped up occasionally, maybe. It's not one of those things that we've formally addressed. Basically, what you want to do is you want to take an imaginary, this will be the hardest part probably, at least it was for me when I was a kid. The hardest part to really get your head around is I have to cut the domain so that the functions are inverses of each other. And so I say to myself, if I were to cut this half, don't do this, by the way. But if I were to cut that, I don't feel comfortable saying that those are inverses about this line. Can you agree with that? So when we do a domain restriction, what we want to do is we want to make sure that we restrict the domain so as to preserve the symmetry, right? And so I don't want this to be arbitrary. I'm not just going to pick one side and murder it. What I'm going to do instead is I'm going to murder off this side of the function. And then we'll talk in a minute about the notation and how do we denote that. But you'd have to agree now that those look pretty inversey, don't they? Right? So having said that, let's talk about the domain restriction. So what we did, first off, I don't want to be presumptuous. Are you okay with what I just did? Took it like a big imaginary pair of scissors and basically just felt like, here I go, boom, and I snipped half of the graph off. And sometimes you have to snip the original function, and sometimes you have to snip the inverse. It just depends on the situation. But in this case, we have to snip the inverse, the purple one. So I'm going to head over here. And when I found the inverse, in order for these to be functions, next to it, I have to put a domain restriction. I have to say that this function is defined over the interval of x's such that, sorry, I don't know why I'm using that fat pen. That's annoying. And I'm going to switch colors too. I'm going to use green. How about this? We're going to say that this function is defined on the set of x's such that x is greater than or equal to 0. So this whole thing is the function. I had to place that stipulation on that function to ensure that he would actually be the inverse of his homie up above. Without that restriction, you would have a full parabola and then that one half graph that comes from roots, and you can't say that they're symmetric to each other. Is that confusing? Not bad? It's that thing I wrote in green. That's kind of new language for you guys, and I'm going to kind of write it and say it again. So here it goes. You just kind of listen to my words and watch my pen. It's the set of x's such that x has to be at least 0, close set. So we use that set notation here. Okay. 2 down, 2 to go. Still rocking it? Feeling good? Okay, let's head on to number 3. And again, I didn't follow my own directions. I didn't graph the line y equals x, but I think it's pretty clear that we're going to be just fine here. So if you graph the line y equals x, you can see pretty unmistakably that those are inverses of each other. That's what we're looking for. You'll see it's a real visual telltale thing when they're inverses of each other. They'll literally just snake around that line. It's a gorgeous sight to behold. All right, next one. Let's begin by finding the inverse. And this one will probably make a table. I got to be honest, man. This is a kind of a freaky graph. So this will be the first one where you'll actually see the XY table. It's just a nice, safe way to do this. Inverse. Let's swap them. So we have x equals the cube root of negative y plus 3. This kind of feels like the last problem we did, huh? What are we going to do next?
A cube.
We're going to cube both sides. So we wind up with x cubed equals negative y plus 3. And then from here, you do have some options. Since this isn't your first time doing what we call algebra, I would venture to say that you'd be comfortable if I put the y over here and the x cubed over here. Like I know I want y to be y equals. I don't want negative y. So that's why I would proactively sort of move him to the other side. And then whatever happens after that is just kind of collateral damage. All right. So the inverse, I would say, is k inverse of x. And he is the opposite of x cubed plus 3. And I, again, I'm going to delete some work. And I'm going to pull this up here. And here we go. So I don't see any issue with my color coding, so I'm just going to kind of be consistent with this. Again, I'll have red graph and purple graph. So I think a table would serve us well. Does anyone remember generally what a cube root graph looks like? Yes, it's the squiggly snake, but laid on its side. The trouble, what we're getting into here, and it was amazing how clear this became last year. With my class, I was really pushing them hard on graphing using transformations. And I just acquiesced at some point. I was like, you know what, you guys are right. It makes more sense to just make our graphs with tables. It's more empowering, like it opens up way more possibilities for us as mathematicians, and it's safer. Making a table is safe. I mean, unless your basic skills suck, but I don't think you'd be here if they did. So what we're going to do instead of worrying about what kind of graph it is, like having it in the back of your mind is awesome, but we're going to make one of these. We're going old school here. So I'm going to go in red and I'm going to say x, k of x. And you're going to help me with this. So while I pour myself a little bit of coffee, I'm going to ask you to give me a good value of x. This is not arbitrary. This is not just pulling a number out of thin air. Give me a good x and tell me why it's good. You want 8? You want x to be 8? That won't do me any good. Right. Good team effort there, fellas. So that was awesome. That's how we learn and that was so beautiful how that dynamic happened. So yes, I want what's in here to equal something that's cube rootable. So it's not about what x is, it's about what the result of that is. So give me an x that would work. 2 is great. I love 2. And the math of it now is this. If you put 2 where the x is, you math it out. What's negative 2 plus 3? And what's the cube root of 1? Boom. That's powerful. That's how you should understand that's your bailout. Someone says make a graph, there's nothing stopping you from making a table. And again, the only thing that would hold you back would be your basics. So 2 to 1 right here. I'm going to stick a point there. Nice. Give me another one. I like -5. And I'm not going to discount what you said. I think we can fit it on there if we freestyle a little bit, don't you think? I think we can go out to 11s. But let's get back to Brenna's. -5 is dope because if you put it in place of X, what's the negative of -5? It is 5. And what's 5 plus 3? And what's the cube root of 8? So we just found another point. So -5, +2. Awesome. Just like that. Anderson said something a minute ago. I believe he said 11. Is that correct? And you might make the case that I can't go there, but you can. You could just eyeball, where 11's at. It's right there. So if we put in 11, what's -11 plus 3? And what's the cube root of -8? No, is -2. So we just found another point, and it's 11, -2. So I'm going to go right to what I perceive to be 11 and down to -2. And I would be willing to bet that that's pretty dang close right about there. So it's starting to generate itself, but we're still missing, at least in my opinion, a couple of pretty critical points. So we have forced it to equal 1. I did right. But how could we force that red egg up there to equal -1? What would X have to be? Here, I'll help you. Put 4 in. Put 4 in place of X up there. I need to get rid of my egg. Sorry about that. Put 4 in place of the X. What do you get? -4 plus 3 is -1. What's the cube root of -1? -1. We should always strive for enough points to have, like, you want to connect as many dots as you can. Any connect the dots artwork is going to look better if you have more points. And so now I can go to 1, 2, 3, 4, -1. And then I do believe we're missing 1, and that's the kind of hitching point. And I think you're going to find that at 3. Because if you put 3 in there, what's -3 plus 3? And what's the cube root of 0? 0. This completes realistically the points that we could expect to find on this size of a grid. But man, that's powerful right there. Like, we could have talked about it, like how it's shifted, it's shifted 3 units to the left and it's flipped upside down and this and that. But at the end of the day, that's pretty powerful math right there. Okay. So now your job is to try to connect the dots. And all I can say is, yeah, good luck. Oh my gosh. And I know you want to watch me do this, but you really should be doing it on your own papers too. So, all right, that gets a B plus. All right, now it's time to do the other one. And the other one's going to be a more comfortable go because we're not dealing with any roots. We just have to be aware of not getting our numbers too out of control. So now I'm going to switch colors and we're going to make a second table. And this time we're not going to call it X and K of X. We're going to call it X and K inverse of X. Like this. So again, give me some good X's. There's a few that'll work well here. Not a ton, but a few. A 2's fine. So if I put in 2 and I take 2 and I cube it, I get 8. Slap the negative on there. It's -8. -8 plus 3 is -5. That's a winner. So 1, 2, 1, 2, 3, 4, 5. Skip it. Pretty good. Did you say -2? So if you put in -2 and then you cube it, -2 cubed is -8. Apply the other negative. The negative of that is +8 plus 3 is 11. So that one's going to be up here. And you said -1 is going to be a good guy?
Yeah.
I agree. -1 cubed is -1. Apply the other negative, you get +1 plus 3 is 4. Sure, let's do 1. Cube it, you get 1. Apply the negative, you get -1 plus 3 is +2. So 1, 2 is one of our points. And I believe there's one more. 0. What a great idea. Let's put in 0. Cube away, baby. Like 0 cubed is 0. The negative of 0 is still 0. 0 plus 3 is, of course, just 3. 0, 1, 2, 1, 2, 3. And I believe that is, again, enough structure for us to say we've got you. You know, if someone put a gun to my head and said, no, find me more points, could I? Sure. But I tend to prefer, when possible, to work with easy points. Boy, that's just a terrible graph. But I'm moving on because I want to get to problem 4, so I don't care. Got it?
Mhm.
Anyone made any sort of observations yet?
It's pretty.
Right. So I'd say we're 3 for 3. That one, I say mine kind of got hit with the ugly stick there at the end, but it still serves its purpose. Let's power our way through number 4, and this will be the hardest one of them all. And then there will be some conversations that we have to have after this about things you notice. And I'm not going to poo-poo the things that you're going to notice. They're smart things. They're just intelligent times to use shortcutty things and not so intelligent times. So whenever you're ready. Right, good for you. So you guys know that this is of the exponential family. You know that the inverse of an exponential is a logarithm. So let's get started. So if we switch the variables, we have x equals 2 to the y minus 2 minus 4. And there is a very specific order that you got to do stuff in. What's the first thing we got to do? Got to add that 4 to both sides. So now we have x plus 4 equals 2 to the y minus 2. Next step. Log base 2 both sides. Good for you. Good. So if I log base 2 both sides, it's going to look like this. It's going to say log base 2 of, you need parentheses, x plus 4 equals y minus 2. Because as you know, the log base 2 on the right cancels out the 2, and then you just drop the exponent down. Right.
Sure.
Last step?
Subtracted.
No,
Let's see.
add 2. I'm ashamed to do all that great upper level math and then subtract 2 at the end. So we wind up with J inverse of x is going to equal log base 2 of x plus 4 plus 2. And I, again, since I'm recording this, I'm going to delete all of my work and I'm going to shift this up. So let's do this. I don't know if I have time, but I'm going to try. 9 minutes is an eternity in my world. So I'm going to start with red and I'm going to do x and j of x. So this is like OG input output, you know, like function input output, like original function. And then the other table is always going to be like the inverse function. So give me some, this is the easier of the two, and do focus your attention at the top, right? We are not working with the purple function. We're working with the red one up there. So give me an X. I'll take it. I like 0. And so this is going to be a little bit of a pain. If I do 0, 0 minus 2 is negative 2. So I have 2 to the negative 2 minus 4, which is 1 over 4 minus 4, which is 1/4 minus 16/4, which is negative 15/4. You might say, well, how am I supposed to graph that? And my answer is, well, just go like negative 3 and a bunch. Just don't make it to negative 4. That's all, right? Negative 3 3/4. Maybe having survived what we just went through, maybe we'll think a little bit harder about the x's that we choose. Give me another one. Two's better. And one's going to put us in the same boat as what we just went through, but I'm down. But anyways, let's do 2 while we're here. So if I do 2, put 2 up in the exponent. What's 2 minus 2? And what is 2 to the power of 0? No, it's not. It's 1. And what's 1 minus 4? I much preferred that experience. That was a lot. I mean, it didn't bother me, but I know you guys don't care for those negative exponents. Andrew said 1.
We don't have to.
But he's taking it back. He's
Yeah.
recanted that. So maybe we should try something crazy like, oh, I don't know, 3. Sound good?
That's what crazy.
So we're living on the edge. I want to progress in a sensible direction here that's going to keep me from feeling pain. 3 minus 2 up there in the little baby power is 1. What's 2 to the 1th? And what's 2 minus 4? Negative 2. Let's keep riding this, man. Let's keep going the correct way. 4. What's 4 minus 2? What's 2 to the tooth? 4 minus 4. Let's keep going. 5.
2 to the third is 8.
2 to the third is 8, and 8 minus 4 is 4. And I think our luck is pretty close to running out right now. I think we might have just spent our last coin here. 6 minus 2 in the power is 4. What's 2 to the fourth? 16 minus 4 is 12. So I'll put it here in case we want to know.
Go back to the office, please.
That point's clearly going to go a little bit further off the grid, but could we do it? Yeah, we could freestyle a little bit. So let's plot some points. And I'll zoom in on this, and you guys will probably have to read me some numbers since I'm zooming in so far. So the first one we had was, I believe, 0 and negative 15 fourths.
Yep.
2, 3. So on your graph, it should look about like this. It's negative 3 and 3/4. Good, good. What was our next point?
2, negative 3.
2 and negative 3.
Mm-hmm. 2.
Next point.
3, negative 2.
3, negative 2. Next point.
4,
4 what? 0?
0. Yeah.
Okay. Next point.
5, 4. And 6.
So 5, 4 is another one.
12.
And then 6, 12 was the one where we're kind of pressing our luck here a little bit. But if I wanted to do 6, 12, I could go to 6 and just kind of improvise and just kind of follow the vibe of the pen. Like there's 9, 10, 11, 12, and just kind of guesstimate where you want it to be. It's not a crime. Just a little bit something to hold on to there. So what you're seeing here, you remember this word. Do you by chance remember what this landing strip is called? You've heard this word last week. I mean, yeah, it starts with an A.
Anderson.
It's, I believe it's this line right here. And normally when you graph, you will make that line dotted. So I can fix that for you. I can make it dotted. That red dotted line has a name.
It's AM.
That's the word. It's an asymptote. And so you're seeing here, by the way, newsflash, all exponential and logarithmic curves have asymptotes. All right. Logarithmic curves are going to go the other way. They're going to have vertical asymptotes. Exponential curves have horizontal landing strips. So if we were to go down that same road that Sutter sort of accidentally started us down, like if we put in a -1 for X, we're just going to keep getting closer to this. And if we put in -2, we're going to keep getting closer. And we talked about this the other day, how that plane is trying to land. And it's so weird. It's always getting closer, but never lands, which is really trippy. So this is what the graph of the red function looks like. And I'm going to move ahead just because I want to make sure. So at your leisure, when you get a chance, sketch this. Good luck, right? And now I want to look at the other function, and that would be the purple one. So y'all can see what the shape of this is going to be. As far as the purple one is concerned, let's make another table, and the table will be titled X and J inverse of X. This is not little kitty math anymore. Like there's a lot of stuff that you have to know in order to be able to navigate these waters. So what I want, and this is a really important thing, is I want that green egg to have a good value with a log base 2. So for example, I would love it if I could make the green egg just equal 2. Because what is log base 2 of 2? 1. It's a redundant log. Log base Zane of Zane equals 1. Log base 5 of 5 equals 1. That's redundancy. And so log base 2 of 2 would be great. What could I put in place of X to make that happen, to make that a reality? -2 is awesome. And then -2 plus 4 is 2. Log base 2 of 2 is 1 plus 2 is, bam, 3. We just got ourselves a point. Let's do it again. What's another good number that I wish the egg could equal for me? You cannot have log base 2 of 0. It's undefined. But the argument cannot be 0, but the argument could be 1. Could I make that green egg equal 1? Sure, I could. What would X have to be? -3 then must be a pretty good X value. You got to know your logs, though. If you put in -3, what's -3 plus 4? 1. What's log base 2 of 1? 0. Any log with an argument of 1 is equal to 0, and 0 plus 2 is 2. What's another good thing that I wish the green egg would equal for me? Keep them coming.
Beautiful.
It cannot equal 0. A
Oh.
log cannot have 0 for an argument, but 4 is a gorgeous thing to say because log base 2 of 4 is evaluatable with just my brain. I don't want to type it in and get some decimal in a calculator. What makes the egg equal 4? 0 then is a great X value. 0 plus 4 is 4. What's log base 2 of 4? If you don't start answering these questions quicker, we're going to have to go on a sidetrack tomorrow and just practice our logs again. I was hoping that these would be quicker. You guys should all be knowing that log base 2 of 4 is 2. And that should be happening quickly because when I ask you for log base 2 of 4, I'm asking you what exponent do you have to put on that red thing to make it equal to big number? Got it? So don't forget what logs mean because we want to be quicker with this. We don't want to be so slow. So if we do a 0 plus 4 is 4, log base 2 of 4 is 2, 2 plus 2 is 4. What else would I love it for the green egg to equal? What's something else that has log base 2 of agreeable? What'd you say? It is 8. Could I make the green egg equal 8? Sure, I could. What would I have to put in place of X? 4. 4 plus 4 is 8. Log base 2 of 8 is 3, and 3 plus 2 is 5. And I do have to interrupt myself here just because the clock is at the end of the day the ultimate boss, and I don't want to keep you late. There are 35 seconds until the bell. So I'd say we'll wrap this up tomorrow, and then tomorrow I'll have an assignment that'll look pretty much just like this. All right. I won't even post it today. There's no point. Sorry for the long lecture. Certainly not the first time, and it certainly won't be the last time.